kind of like re-engage with what our purpose is here, because it's really easy to get lost in like, all right, let's zoom in here and write down a number and look at this graph and write down a number and do some computation. So our first test, we spent a lot of time prior to that talking about what is constant rate of change. And we had a whole bunch of examples. We talked about how we can use constant rate of change. If you know a variation in one half of a constant rate of change relationship, you can multiply it by something, the constant rate, in order to get the other half's variation during that corresponding interval. Whatever two amounts of change, if one thing causes change in another, or two things vary in a related sense, then if it's a constant rate of change relationship, there's this multiple that tells us how a variation in one multiplied by something equals the variation in the other. So the thing is that that's kind of limited if we just restrict ourselves to situations where it's like $2 per gallon for gas all the time. It has to happen all the time, no matter how many gallons of gas you get. Because there's a lot of situations that aren't one constant rate that happens all the time. And this example here is something that, in reality, this isn't a straight line anywhere, but if you look at it in small enough chunks, it can seem to be close enough to, or you can continue making your chunks smaller and smaller, you can make it essentially constant rate of change over intervals if you look at small enough intervals. And why is this okay that it's essentially constant instead of exactly constant? Well, it depends on what you need to do. So if my goal is tell somebody how fast Usain Bolt is running, if I have a small interval, I can say, well, at this moment in time, he's running at essentially a constant rate of 6.8 meters per second or whatever. Like, well, how do you know? Maybe he changed a little bit. Well, okay, if it's about 6.8, maybe I can make it a smaller interval and say, okay, if I look at a smaller moment and look at variation within the smaller moment, maybe it was really 6.79 meters per second. It's like, well, does that make a big difference in the scope of the world? Probably not. So if you say about 6.8 meters per second, then that's a good enough answer for that. Depending on what your needs are, though, if you can see, you could continue zooming in farther and farther and farther and farther and make something that, as you vary through that interval, you can make it so that to whatever degree of accuracy you want, 2 decimal places, 3 decimal places, 4 decimal places, as you see that variation, you could continue zooming in farther so that whatever interval of dx you're concerned about being small enough for your needs or having an accurate enough need, you could pick an interval that's small enough so that it'll be that level of essentially constant that makes it exactly constant to your like 4 decimal places of accuracy or 7 decimal places of accuracy or 100 decimal places of accuracy. In, well, not every single case, but in most normal cases, in most positions. So we'll take a look at this, but just one of the things I believe I asked you to read this prior, was about things where there isn't a rate of change at every moment, where if you zoom in, no matter what you do, it's not becoming closer to a straight line. It doesn't look like constant rate of change. Section 4.6 in your book was about this. And there's an animation here where, let me make this bigger. We can see somebody playing around with GC and zooming in, and this looks like an absolute value graph. Yeah, y equals absolute value of x minus 2 plus 1. And I know that the sides of that are exactly constant rate of change. One constant rate of change on the left half of that vertex, another on the right half of the vertex. But no matter how close I get into that vertex, no matter how close I zoom in, and you can see maybe that in this video, where I can pause it, that the y values here, 0.99999 to 1.00001, that's extremely close in. As many decimal places of accuracy as I wanted to let GC take me to, no matter what I do, that is not going to look like a line around that vertex of the absolute value graph. And you know that it behaves that way. You've talked about absolute values, that there's a sudden change in how absolute values are defined. At this case, at x equal to 2 is the dividing point between when I do one thing and when I do another thing with absolute values. If you take an absolute value of something, if it comes out negative, If you're taking an absolute value rather of a negative expression, you make it positive. If you take an absolute value of a positive or zero expression, you leave it alone. And that changes suddenly, and there's nothing we can do about it at this one position in the graph that corresponds to x equals 2. And you can see there that this is zoomed in so far that the y values just all look like 1, which looks ridiculous. 1, 1, 1, 1, and 1. But it's just 1 point, so many zeros that the last one is past the degree of accuracy this document was set to. So not everything has this ability where you can zoom in as much as you want and you can find a constant rate of change, but lots of things do. And this graph, everywhere except for one particular x value, has, well, actually constant rates of change. One on the left and one on the right of x equals 2. In the next section of the textbook, which I didn't ask you to look at, because it looks kind of like a mess. It explains these summations, but there are certain sorts of functions that are highly unpleasant, actually. Let me look at the next section. Infinitely wrinkly functions is the name of it, which is kind of a fun name. But this end, okay, it looks kind of bumpy, so let's zoom in. Let me make this larger. This is called the Blancmange function. But zooming in here, okay, bubbly, bouncy, whatever. It's the closer I get, the more mountains I see in this. If you can see the y values in this, they all look the same again. It's a little bit smaller because the stuff is up above, 0.533333. This is zoomed in so far, no matter how far we go with this, it's not going to solve the problem. This is something to do with, as you can see, really ugly function definitions. We're going to talk about using sum notation a little bit. I'm not going to make you write anything like that, but we're going to use this to express constant rates of change, sort of MDX sort of expressions, where instead of having one rate of change that works wherever I want it, I'm going to have a variety of different values for m, the rate, depending on where I'm looking. Because although something like this function is kind of useless, like I can't, like if this was Usain Bolt running, I don't know what's happening. He's like in a popcorn popper. No matter when we stop, he keeps changing speeds, magical like that. But for normal sorts of functions that you've dealt with most of your life, if you zoom in close enough, you can find this constant rate of change. And constant rates of change, like we used on our last test, you can do to figure out, okay, so if I know how much the independent variable varied, based on knowing a constant rate, I can use that for a little bit and figure out a change in my dependent variable. And then I can repeat that process again if I'm concerned about, well, maybe the rate would be better estimated by a different number now because I'm actually looking at something that isn't one constant rate, but maybe different sections of the graph seem to be close to different constant rates if I zoom in on them. And maybe I can just estimate what's going on by using a few different rates. Where we're headed towards is trying to figure out how to look at knowing what all these different potential rates are and figuring out what happens because of that. Like in the first section of the course, we talked about what if the constant rate is 1.7? What are all the things you could tell me about this? Well, we're going to have a whole bunch of rates demonstrated either graphically or in a piecewise function and use those bunch of different rates to help us figure out what happens over various intervals, using parts of that or all of that, or just in general expressing what happens, how much of something I have, how far I've traveled because of a rate of change of something, whether it's gathering money at a certain rate or traveling down the road at a certain rate or whatever it might be. If that rate isn't really the same all the time, but it's not crazy like those last couple functions where there's no way to express rates by zooming in and looking for this constant rate. If I've got something like this, like, oh, well, I can estimate rates at a bunch of times and so figure out, well, how far he traveled. We know how far he traveled. He went 100 meters. He was running a 100-meter race. But in other situations, we might not know that. We're going to start from a different place and work toward getting something like this as a result, figuring out where he was at different points based on knowing what his speeds were. So, in any case, what I asked you to do last time was to look at, I passed out a worksheet, but it's also posted, looking at that graph. We set it up to calculate the m for us automatically so we don't have to keep redoing the same computation over and over. And I want to just kind of look at some of this. So there's a lot of different numbers that you can get here. This requires 1, 2, 3 by 3, 4, 5, 6, 7, 8, 9. 27 different numbers computed in here, which each one of them is looking for at a various x value, at a position on the track, the current value of how far he is from the starting line, measured in meters. We wanted to estimate by using a small change in x, a small change in time, during that time, how far he got down the track, based on calculating in our graph that m, his essential constant rate of change during intervals of 1/10 of a second, 1/100th of a second, and 1/1000th of a second. So within each row, the numbers are going to be kind of similar to one another. But as an example, in class, I believe we worked with a current value c equal to 3. But let me just put this back to the beginning here. So at c equals 0.25, so this m value we set up by filling in the bottom of this. We found our 2 points, defined these 2 points, and then did the y final minus y initial in the numerator, and x final minus x initial was simplified. Change in x is dx, or that variation horizontally in the graph, was dx units between 2 points that are extremely close together. Now this is using a current value of 0.25, which is, if you can see, there's my 2 dots are clear down here. So shift click, draw a box around it. They're very close. So I'm going to zoom in farther until I can see this arrow thing. So you can see that this looks extremely close to being horizontal in the way that the scaling is done here. But looking horizontal, it has to do with your x and y scale, relatively speaking. So, but in any case, I can think about, let x vary from 1/100th or 1/1000th to 1/10th and anywhere in between. At 0, you're not going to get a value for the m, but let's see if I can get this to 0.001. When I'm near 0.25 seconds, a quarter of a second into the race, because of the computations we did to set this GC worksheet up to do computations for us repeatedly, so we don't have to keep pushing the same buttons repeatedly, we have this m, current rate of travel, during this interval, during this small, so I can see this moment that I have set up is from about 0.2488 to 0.2525 over this whole screen width up here. I call that whole thing my moment. I'm looking at what happens within that moment, between 0.25 and a little bit to the right, which, since I'm at dx is 0.001, this is from 0.25 to 0.251, sorry. So x varies by 1,000th of a second. How much did his distance change? Not a heck of a lot, but I can see that the ratio, change in distance to change in time, or the variation in distance that happened during that variation of 1/1000th of a second, that ratio is about 2 to 1. Or in other words, he traveled about 2.10918 times as many meters as the number of seconds that went by. Or, to say that like a normal human, he was traveling at about 2.1 meters per second in this moment. And not just the part that's highlighted with the purple arrow, but since this whole screen looks like about the same thing, I can say, during this moment that I see, 2.488 to 2.2, whatever, I could say his speed is about 2.1 meters per second. So if I wanted to go record things, I could go back here and, let me start this up. There we go. So, so about 2. I always do that. Sorry. 2.1 approximately, and I said the more degree of accuracy than that, but about 2.1 meters per second. Remember, these are m values we're finding, so these are his rate of change, his speed, or how many times more the number of meters is than the number of seconds that elapsed. And we're looking at a small amount, but this 2.1 times as many meters as there were seconds in that little purple highlighted area. So, in any case, we can go through and do this. Like I said, there's 27 of them, so I don't want to go through each one of them. It's kind of repetitive. But what's interesting is when you have this done, you can see some interesting patterns in what happens. Because the numbers within each line are similar, but they're not the same. A lot of them follow the same pattern as one another, but not all of them. So I want to take a look at that here. I've got the answers written out here. So I rounded these to 2 decimal places. But looking at these rates, so depending on what length of time interval I'm looking at within a moment around a quarter of a second into the race, depending on how long a moment or how long a variation I choose in my time interval, I get between 2.1 and 2.4 meters per second. And that's kind of different. So in terms of accuracy, like, well, when I'm thinking about closer to a quarter of a second into the race, I think about a smaller interval. But again, that speed then only pertains really in that very small moment. So it's all kind of a matter of what you're trying to say. Right near, extremely near to time 0.25 seconds into the race, he was moving at approximately 2.1 or 2.11 meters per second. These are all really average rates of change, as we talked about on Monday. So if I were to look a tenth of a second farther, so from 0.25 to 0.35 seconds into the race, his average speed was this 2.42, which is maybe noticeably larger to even, I don't know, to the naked eye. That's kind of hard to say, like 2.4 versus 2.1 meters per second. But that seems like quite a bit faster. So I can see by that, oh, if I look at an average speed over this interval that goes farther into the future and it's larger, we talked about this on Monday, but that must mean he's speeding up. So in the graph, it kind of looks like he speeds up and then just kind of stays at a constant rate for a long time. Because it looks pretty much from a distance, if you look at the full 10 seconds in the graph, 9 point however many, it looks pretty much like the end of it all looks like a straight line. But I know it's not. If you look at these numbers here, now this isn't every point in time in the race. There are infinitely many points in time during the race. It's just a few selected ones here. A bunch near the beginning where the shape was changing more, where maybe I'd think, oh, well, I better recalculate. He seems to have sped up. You don't have time to make that whole statement before you finish the race, but the little zapper timers at the track can do that. So if you look at these speeds, 2.1, 3.6, 6.0, 7.9, I can see from those, looking from one point in time to another point in time and calculation over smallest, these are the smallest size intervals at those times, I can see that he's speeding up from that. But I can also see, like, for instance, just looking across one row here. If I look at an interval of time extremely close to time 2 seconds into the race versus looking from time 2 to time 2.1 into the race, I get a larger average speed between 2 and 2.1 than I do between 2 and 2.001. So if I go farther into the future, I get a faster speed. Must mean he's going faster later. So these are all just averages, but this is an average over an extremely small interval as compared to this one. So I can see by looking at the progression here, as I go farther ahead of 2 seconds, by going to the left here where my intervals are larger, we can see that he's accelerating just from one set of estimations around time 2. So most of these are like that, where the dx at 0.1, dx equal to 0.1, or using a tenth of a second interval, gives us the largest result. But if you look near the bottom here, between time 5, 7, 9, if you look at 5 seconds into the race, all three of those are about the same, 11.90 to 2 decimal places, 11.90 and 11.91. What would that maybe indicate about what's going on? Although that's his speed approximately, but what would that maybe indicate as compared to the previous ones? Yeah. All right, so yeah, he got his speed up to about 11.9, but going forward in time a little more, yeah, he's accelerating less, like hardly noticeably if I go to this whole tenth of a second ahead. Or maybe even if you look at the next ones, the next line's kind of the same, 12.49, 12.49, 12.50. Hardly faster if I use that larger interval than if I use the small one. Look at the last line though. 11.76, 11.75, 11.69. As I go farther and farther into the future from this 9 seconds into the race, you finished in 9.58 seconds. 9.68, 9.58 seconds. So none of these go past the end of the race. What's going on in that last half second of the race, though? Yeah, he's slowing down. Probably he was winning by so much. I'm like, turn around and look and see where everybody else is. Yep, I'm done. I'm going to win, so we're done with this. So he stopped accelerating for sure by this last second into the race. You can tell because by looking farther into the future, you get lower values for his speed. So you can call it deceleration or negative acceleration or whatever. But you can see the pattern of his speeds and see that he was speeding up, speeding up, speeding up. And this is really hard to see that just looking at that whole graph, it looked kind of like a straight line. So he got to one speed and he just kept running at that speed. That's the danger of looking at a graph shape and trying to guess what's going on. You really need to have some more details, ways to calculate, look at some values or some knowledge of what's going on to be able to see all these details. But in any case, past all of this, the point of this top half of the graph, and we'll get to the bottom half in a little bit, the point of the top half of the graph is because of the way that he was running, which was nothing like an absolute value graph or that kind of bouncy blancmange function. Blancmange is a type of dessert, kind of like a jello mold sort of thing. But he wasn't running like that. He was running at speeds that when I zoom in close, it looks essentially like he's running at a constant speed. Now, if I look at large intervals, not so much, or relatively large intervals. But if I look at small intervals, I can use these computations to tell me essentially how fast he's going, and that seems like a reasonable thing to do. Same as in your car. Your car has a speedometer, tells you how fast you're going. If you stop to try to figure out how fast you're going, it goes to 0. So you have to look at it while you're moving, see the speedometer. It actually, well, it used to be a mechanical process. Now it's all computerized. But nonetheless, it does require knowing something about the size of your wheels, at least the size they're supposed to be, axle turning around, and figuring out how fast you would go a certain distance because of how many spins we go and how big your tires are, how far forward you'd go in a small amount of time. It's not measuring like at one instant. Can't do that. If you're looking at one individual point in time, there's no speed associated with that. We assign a speed to that by looking at a small moment, including the time that you're interested in. So going back to, we'll get to the bottom of this sheet in a minute. We're going to take a look at what these rates look like. But what I want to do is talk a little bit more, linking this back to what we were doing with one constant rate all the time, linking back to that. So let's see. Oop, that is not what I was trying to click on. This is what I want. All right, so I think we talked about this, but all right. There we go. So I think I had this up on Monday, but just to repeat, dx, when we used this prior to our last test, we said it was small, but we didn't always necessarily use it as small. We didn't worry too much about how small is small enough because we actually had one constant rate of change that extended for our entire situation. So if we want to be able to use this in more situations, we're going to be stringent with this. Okay, dx is going to represent from now on for these situations where I can't guarantee always constant one rate all the time. I want to use just small variations in x. How small? Depends on the level of accuracy you want. But small variations in x, and call that dx. And another word for this, when we're specifically talking about it being small, and we did use this word also before, was this differential in x. And similarly, a small amount of variation in y, or whatever letter, I would call that a differential in y. Whatever letter it is, the letter chosen isn't important, but it does represent change in something, so it would be only something we apply to a variable. So I can have a variable and talk about its overall value, and then I can talk about changing the value of that variable. If I change it by a small amount, I talk about the differential of that variable, or typically write it as d something, d in front of the thing that's changing. And that's a concept that you ran across before, but we didn't always need to stick to it being small because of the examples we were working with. So when we are using these dy and dx, their usage itself, when we're talking about a relationship between dx and dy, the usage of this notation implies that we're talking about a constant rate of change, not over everything, but within that dx and the dy, within a moment where we're using a variation in x. If I'm going to talk about the variation in y that goes along with that, I base it on having a constant rate to use within that moment. So if you see dy's and dx's, or whatever the variables might be, d somethings, keep thinking about your constant rate of change relationships, that dy equals mdx for some value of m, and I can compute values of y by having some place to start with, an initial value of y plus a change, which I can compute mdx. So dy, in other words, needs to be a constant multiple of dx as it varies within our moment. We get to pick the size of moment that we want to make this reasonable, or to make it a reasonable estimate, however you want to think of that. So we did a lot of problems with, let's see what I said, we had boxes of candy and buying some gasoline and lowering a flag, and some other examples of constant rate of change for a long period of time. Let's talk about Usain Bolt and use some of the same computations and review our notations that we used for these and solve some similar sorts of problems. So here's the same picture, snapshot of a section of Usain Bolt running between time 0 and about 1.5 seconds. So just a little snippet of this race. So this description at the top is just the same description we've talked about. Suppose this is a graph of function f relating his distance from the starting line, the y variable dependent, to the time the race started, x. So our y is measured in meters and x is measured in seconds. And the displayed graph here near x equals 1, so where this little black dots are here. If I were to zoom in really close, we could do that again, but I'm not going to redo the zooming. But you can imagine that. We know what it looks like around there. It's essentially linear, meaning if I zoom in, it looks like a straight line to the naked eye. And I can even have GC do some computations where I can see that m, the constant rate relating x and y as it varies near time 1, isn't changing a whole lot. And I can zoom in far enough so that it can not change as much as I want it to not change. So pretend that we're going to let x vary from 1 second to 1.006 seconds. So that's a very small variation in x. And during that time, so you don't have to pull out the GC worksheet and calculate this, I'll just tell you that his distance from the start varied from 3.4882 to 3.5251 meters. And if we wanted to calculate his speed at time 1 second, thinking about, oh, this is a very small change in x and a very small corresponding change in y. The size of the change in y depends on what this m is and the change in x. So what would I need to do to calculate his speed at this point in time? What could I do? This is what your GC worksheet was doing. But if I wanted to calculate this using this particular 0.006, that wasn't one of the values that was on the worksheet that you filled out, but if I want to calculate speed, I need to know how far he traveled and how long it took. And maybe the how long it took is something easy to do without a calculator. 0.006 seconds. In that particular 0.006 seconds, he traveled, maybe subtract these, 0.04 something meters. So we should be able to get a computation for speed. We just need variation in y divided by variation x, dy divided by dx. Over this small interval, we know that he's traveling at about a constant rate. We could zoom in and do this, but if I were to look at the graph and extend from 1 to 1.006, I can make the measurements that I need. And here, trying to pause this. Make the measurements that I need, but all I need to do is, and this is going to jump back and forth for a second. all I need to do is calculate my dy, my change in or variation in distance from the start during this small amount of time, 3.4882 to 3.5251. I can calculate dx, 1 second to 1.006 seconds, mentally. Dx would just be 1.006 minus 1, so that's 0.006. My constant rate would be m, otherwise known as dy over dx. And I don't know what that value is off the top of my head, but that's a quick calculatory thing or GC thing that we could do just to get a quick, it's just a quick result there. Dy over dx, or the ratio between the changes in its distance and the elapsed time. So these other questions, which appeared a second ago, let's think about, for this specific problem here, how to symbolically represent all of these bits and pieces. So some of them I kind of scribbled up above, some not. But if I wanted to represent the initial value of the independent variable, so what symbol do we typically use for initial value of independent variable? Yeah, xi. So what about the value of that? What is the initial value of the independent variable? What is xi in this situation here? 1, right? So value-wise, it's 1. Second is the units on that. Symbolically, it's xi. So see if you can go through and do the same for 2 through 6. No, there's not a symbol for what a moment is. See if you can figure out for this situation, where I did some computations and wrote a few symbols up above. But think about values, think about symbols that we use for these. Let's see what you can get. I think you know them. If I can get this thing to play again, that'd be nice. Nope. Trying to get that to play, but it won't. All right, so what about the initial value of the dependent variable? There's a couple ways we could write this, actually. Initial value of the dependent variable, kind of similar to how we did the last one, could be y initial, or we have a function name here. How could I write it using function notation? Okay, f of xi. What is xi? 1, f of 1? Now I know the value I have over here, but I could express that value f of 1, f of xi, yi. I could talk about those. Any of those mean the same thing. Since I have a function name, I could use function notation. What about differential in x? Symbol for that is dx. If you wanted to say x final minus x initial, you'd say that. What's the value of it? Yeah, 0.006 seconds. It's that 1.006 minus 1. So dx would be the shortest way to write that, but dx means the same as x final minus x initial during any interval that we're considering. Or maybe it's a x current minus x initial, like x minus a number 1, if we're thinking of something where the variation is still in progress. Differential in y, what does that differential in y value turn out to be? How many meters? Yeah, 0.0368 meters. And the symbol for that, dy, y final minus y initial also. If you knew the constant rate of change, you don't necessarily have to know y final to find y final. You can find it. If you know you've got a constant rate of change over a small increment, you can use that constant rate to produce additional values. So in this case, we didn't know it in advance. We're supposed to be finding it. That's the last question is here. If I want to talk about the moment, what I wanted to point out about this is the moment is just, it's kind of, it can vary a lot from person to person, how you define what your moment is. But think about this second graph over here. Think about visually, if you want to pick a moment, pick something where if you look in that close, it's going to look like constant rate of change. So I wouldn't want to pick 0 to 1.5. Time 0 to time 1.5 when I'm looking at this graph, I can pretty much see that there's a lot of variation in the rate. So there's not a constant rate between that. But this graph over here, or some interval around x equal to 1 that's much closer in, it looks like a constant rate. So just using this picture, I'd say about 0.99 to 1.01. If I zoom into that specific window, if I zoom into that level of, look into that level of zooming, I don't know what kind of English that is, but if I look in that close, then it looks to me, maybe to you, like it's a straight line. So it looks like something that represents constant rate of change. Now, is it over that whole window? No, it's certainly not. But if I look at small enough parts, I can find rates that stay constant within small variations of x to whatever degree of accuracy I want. If I want it to stay constant to 4 decimal places, I can get that. I can zoom in far enough to get there, and so forth. So in any case, there's not a symbol for moments. And like I said, moment is just kind of a concept of look at a section, see what happens. Look at a section. If it looks like a straight line, that's a good moment to choose. If you're doing computations on GC as opposed to just visually, you might want to check to make sure that your dx value is small enough as you let that vary within the moment that your rate isn't all over the place. The rate of change at this moment, though, just symbol-wise, m or dy over dx. Yep, and about 6.1 something. Yeah, depending on how many places of accuracy you kept things to or if you rounded things off differently, but just over 6 meters per second when we're around time 1 second into the race. All right, so in the graph, because I didn't do this part, so there's parts A, B, and C. Find the value, how it's represented, and then in this graph here. Now, if I can get this graph to play again, here, I'm going to start this. There we go. So if I'm looking at this graph here, I can pause it in a more appropriate place so I can see some things. All right, so we've got the initial value of the independent variable. If I want to represent that in this graph, sorry, messy program. Initial value of the independent variable on the function, I can see that here. But if I want to find that value, I'd be looking down here. I have to look to the axis to see what the value is. At this point, there are 2 numbers going on. It's a correspondence point between 1 and f of 1, which we were told what f of 1 is. It's the distance from the start at time 1 is this 3.4882. But our x initial value can be seen down there all on its own. Similarly, our y initial value can be seen over here all on its own. Both of them appear at this point. But in any case, the differential in x, what aspect of this display here is how we've represented the differential just in x on its own? Is it something on the axis? Is it the blue line? Is it the arrows? Is it where's the differential in x seen? Arrows, which arrow? There's 2. Yeah, the horizontal line that's extending. So it's extending from our initial value out to the right. So this dx, when this was playing, was growing from, looked like it goes from 0, although we can't actually have a change of 0, it would be no change. But dx going from nothing to, well, wherever I stopped the video, goes out eventually in this animation to 1.006, meaning dx grows as large as 0.006. But this horizontal segment there represents dx, and similarly the vertical dy. And the ratio of those two gives us the constant rate of change. There's not a place you can look on this graph to see constant rate. It's not like, oh, there it is. I can see the constant rate. But you can see that as it grows, the dy and the dx maintain that constant ratio. So I guess you could see that by looking at similar triangles, it's maintaining this constant rate. Or just the fact that this graph looks like a straight line within this moment, that indicates that I've got a constant rate. But there's not a way to see the number, whatever we came up with, 6.1 or whatever meters per second. There's not a way to see that physically, but the ratio of a couple of lengths measured in it are going to maintain that. And the fact that this is a straight line means that there is a number like 6 someplace. All right, so the moment would just be the whole right graph there, I guess. Now, let's do a different problem within a different moment. I got to clear this all off. And we'll go to, oops, this guy. All right, so here's a second moment of the graph. If you can see, this is much closer to the start of the race. Got between x equals 0.395 and x equals 0.415, this small moment on the right seems to represent a constant rate of change. So if we want to compute a constant rate of change for any time during the moment, I could, but if you read this up here, we've got that. At x equals 0.4 seconds, Usain's speed is 3.07 meters per second. Like, oh, well, that's how people speak. It's like, all right, so if I wanted to compute that anyway, I'd need to think about some moment near time 0.4 seconds into the race and look at a small interval, compare the distance changes to the amount of time that we'd varied through, and see what that speed is. But same sort of question, different given information. I've got a starting time and an ending time for my moment, as well as a current value of x that's within that moment. And I apologize, on this graph here, there's this little floating df. You can think of that as dy. Sometimes you'll see in other textbooks, so I wanted to point this out, you'll see df instead of dy, like the name of the function instead of the dependent variable. A little bit non-standard, but there it is here. So see if you can figure out a symbol and a value that goes with each of these 7 things. And the last one isn't something that we had to compute last time, for instance. So a little bit different set of things to find. But using our constant rate of change tools, we should be able to do this. So as long as we're within this moment, we can use constant rate of change. So notice there are 4 different points in time that are mentioned. Make sure when you see, there's a whole bunch of different times. Don't let that throw you off. 2 of them are talking about our moment that we're looking in. The other 2 are talking about the interval where we're measuring change in distance, change in time, and they're within that moment. So if you can see the full graph on the right here, starts to the left of 0.4, goes past 0.415 seconds into the race. That whole graph, that's our moment. When you see these up here, it's 0.395 through 0.415. It's saying that the graph is essentially linear between those 2 values. So that's how we know we're going to, okay, it's essentially linear here. This is going to be my moment. Now within that moment, what's Usain doing? Well, he's running. So here, I'll stop it about there. The moment in question, again, not a symbol, just about 0.395 to 0.415. That's what those top 2 x values at the beginning of the paragraph are talking about. And oh, notice by the way, this is kind of abbreviated definition. This would be not a good, define these variables, x, seconds, y, meters. That's not a good definition of them. The only reason I put that so briefly is because we've been talking about the same thing repeatedly. So just be aware, that's not a good defining our variables here. But in any case, the rate of change in this moment, what's the rate of change we're using in this moment? It's listed this time. Yeah, it's that meters per second would be the units on it, 3.07 meters per second. It says so right here. In this moment, his speed is about 3.07. The point of choosing this large-ish moment is that within that moment, it looks linear throughout. So one constant rate would pertain to the whole thing. We can measure that if we had corresponding changes within that moment. But dy over dx, or m, would be our constant rate of change that we use for the moment. The initial value of x that we're using to compute this isn't 0.395. What is it? Yeah, just a 0.4. So we're within this moment. We're imagining x varying from time 4 up to time 0.4 to time 0.408. And we're going to compute what happens during that interval. So his initial value, the initial value of x, 0.4 seconds into the race, the beginning of when we start measuring things, is that 0.4 seconds. We go forward in time by 0.008, 8,000th of a second. And during that time, this is within this moment where we have an essentially constant rate of change. If I want to find how far he traveled, what do I do? MDX. We've got a rate, 3.07 meters per second. We have a amount of time for this small interval within our moment, time 0.008 seconds. So if you multiply those together, that's just 3.07 and 0.408 multiplied together. So about 0.02456 meters is how far he traveled during that 0.008, 8,000ths of a second. So if he started, as it says here, at time 0.4, or y initial, at 0.702 meters from the start, like in this picture, this is less than half a second from the start of the race. Where was he by the end of that small interval, 0.40? Where was he by time 0.408? Well, here's his initial position. Here's how much his position changed during those 0.008 seconds. So I can think of symbolically his position at time 0.408 is, well, wherever he was at 0.4 plus the extra that we just computed, which would make those two previous numbers added together, 0.02456 added on to 0.702. So not using constant rate of change over a long interval, we were not going to say he did this for the next 9 seconds. He just did this for the next 0.008 seconds. All right, so a couple of things to note. A, on Friday, we were having a written quiz. Covers doing stuff like this. There are some kind of additional practice questions beyond what we just did here, but kind of the same thing. Think about the symbols, how far did you travel, where are you now, those sorts of questions. There's also a Canvas quiz, some of the symbolic representations. So I'll post that all, but the Canvas quiz should be open now through tonight at midnight.
Can I ask you a question? I want to go to the last page.